So my name's Paul, I'm the CTO at Solvexia, and I'm going to give you a bit of an interesting talk today on security. Most people in this room are users of technology, and I think the way you're using technology is just increasing more and more as each year goes by. The number of services you need to communicate with is increasing. And really underpinning all of that is this thing. And this is the only time Google Images let me down. I really wanted to say encryption, but couldn't find a good slide for that. But encryption and security are critical. All of the things you do in your work and all the websites you go to communicate with all rely on security and encryption. So what we're going to do is go and whiz through history a little bit to see how humans have been attempting to solve this problem. Basically, around 500 BC was the first time we have evidence of humans sending encrypted messages to each other. And although the approaches have got more complicated over the years, the risks of doing it in 500 BC were basically the same until about 1990. What happened then? We had some smart mathematicians come along in the 1970s, and they discovered something very interesting to do with prime numbers. After that, we were all safe. First of all, though, what do we mean by encryption? When we say we want to send a message securely, this is obviously happening on your browser all the time with everything you do. We basically want to mean that only the intended recipient can receive the message, and nobody can tamper with the message on the way. And humans have had varying degrees of success of that since about 500 BC. So even though I'm the CTO, I'm proud to say this is the lowest tech demo I've ever done. And what we're going to do is send, first of all, an unencrypted message to someone in the room. And I'm sure we've all got secrets we want to share and things we want to say that are secret. So here's the message I need to send, and you can see why it's very secret. After I started working on this slide, we had a second Jonathan join Solvexia, so I just want to make it clear which one I'm referring to. Okay, so I'm going to do this demo, and I'm going to get Rudy to help me. What I've got is that message written on this piece of paper. Okay, so I'm going to fold this up, and I'm going to give it to Rudy. And Rudy, I would like you to give it to that guy over there, sitting in the row just behind the column. Yep. What's your name, please? Yes, Jacob. Okay, could you go and deliver that to Jacob, please? So I'm sending, hopefully securely, my message to Jacob, and this is what it should say. Could you please read out the message you got? Right. So that was a bit of a fail, okay? What happened there, it looks like my trusted messenger tampered with that message in transit. Didn't get to the receiver very well. So we're going to do another demo now. Where did I put the pointer? Because that was actually the transmission of a physical letter. What we're going to move on to now is the transmission of something digital. And as you know, in the digital domain, you can make hundreds of copies of things all the time. So I'm going to send another message. I'm not going to use Rudy anymore because I didn't really trust what he did. But I've got here the same message again, and I'm going to deliver this one to Roman. So here I go. But as I'm doing this, I'm going to drop copies of this. Of course, they're all landing up the wrong way. I'm going to drop one here, and I'm finally going to give one to my recipient. Can you confirm that that is what is on the screen? Can you also, Paul, did that look the same? So what have I done here? If I wanted to get that securely to this guy, why on earth did I drop copies of this everywhere? So both of these demos were total fails. And you might think, what on earth is Paul doing here? If you wanted to send something securely, you would never, ever do it that way. But my answer to you is that. Every time you see that in a web browser, you have done what I have just done. Any communication you make with a web server over HTTP, you suffer the risk of your message being tampered with, the response being tampered with. And to get from any browser to any web server, you've got to go through probably 20 routers across the internet to get there. Every one of them could be recording the traffic, logging the traffic, and using it. That's my messages across the floor. So if you're using any website that has HTTP in it, you're open for just serious problems. 70% of the top 140,000 websites in the world do not even have an HTTPS offering. HTTP should die. It was a very interesting experiment in 1990 when the web first came out. We should have very quickly moved everything over to HTTPS. There's quite a movement right now to do that, but we're in this kind of weird halfway house where there's going to be a long way to go. You all need to be very vigilant when you're doing anything on the internet that is over HTTP. Something's changed on this slide here. And it's not the fact that when you search for cats on Google, there's 599 million results. Can anybody see what else is a little unusual on the screen? Up in the top left there, there's a green padlock. And you might think, why on earth is that? I'm just doing a Google search. What's happening here is that Google has recognized how important this is. There are some countries in the world where you could be persecuted or go to jail depending on what you type right here in the screen. So HTTPS is no longer for when you are logging into internet banking and those kind of things. It's actually literally for everything you do on the internet. So we're going to do another demo now, but we're not going to be so silly. We're going to encrypt our message. So let's have a look at some encryption. There's an example up there. So I've taken a message and I've encrypted it. It's pretty hard to read. Does anybody recognize what that might be? Very good. Invented by this guy in 1837, it's Morse code. It actually has nothing to do with encryption. It was invented to solve an engineering challenge at the time of how do you send messages over thousands of kilometers when the best thing you were likely to receive at the other end was a blip or a dot or a dash. But there's interesting principles here going on with Morse code that we can take a look at. It basically uses a character substitution algorithm. There's the alphabet of the English language. There's all the dots and dashes. That represents a key. If I was to use Morse code right now to try and send something to somebody in the room, can anybody suggest what would be terrible, what would make that a terrible choice? Sorry? Yes, that's true. So maybe I could use a computer to make that happen fast. Okay, here's a clue. The key is public. Everybody, well, not everybody, there's people out there who know Morse code. There's people who could even read the Morse code across the top. I'd only need to go to Google and get that key picture there, and I could decrypt the message. So what makes Morse code terrible is that everybody knows the key. And this is going to be a theme we're going to come back to do with encryption. The other problem with it, of course, is that it's a little bit too simple. And if anybody wants to know what that says in the top, that says Solvexia does not use Morse code to encrypt your data. Off topic, but Samuel Morse was one of those inventors who was also not just a scientist and an engineer and an inventor, but also an artist. Seems back in those times that was quite a common theme. These days, obviously, things have diverged. But conceptually, what Morse code did there with substituting characters is not dissimilar to what we do today for modern encryption. So let's be a little bit smarter now. We're going to make up our own key. Let's say we write the letters of the alphabet, and then we come up with some sort of substitution approach, and we can take the word hello and represent that as URYYB. So we're going one step closer to some kind of encryption now. You follow that strategy forward, you can start to encrypt a whole lot of sentences, and it's all gobbledygook. Looks pretty good. There's two challenges with this approach. One is making sure the algorithm that we used is complicated enough. The other, and this is the huge one, is safely transmitting the key. Because if I've encrypted a message with that key, I'll have to make sure my receiver has the same key. So let's do a different demo now. So there's our message from before. We're going to encrypt that now. And we're actually going to send that. So here's my message. It's actually not the same as the one on the screen, but this is an encrypted message. So I'm going to choose you on the end up there. Yes, you're the one who just looked around. What's your name, please? Okay, great. So here's my encrypted message. I need one more thing before I do that, I'm sorry. As I deliver this one, I'm going to drop copies again because it's going across the internet. I don't really care. Can you read that? So it's encrypted. I don't care that he got a copy of it. Here's another copy on the floor. This is how the internet works, everybody. There you go. So I've successfully delivered my message to my recipient now. Can you read that message? Exactly. He needs the key. And that's the thing we're going to talk about in the following slides. What I do have here is the key. And you're in the lucky position because the rest of my slides are quite boring. So I'm going to give you this and a free Solvexia pen. And if you follow the instructions on there, you should be able to decrypt that. And on my last slide, I'm going to ask you what it says. Right. So let's look at an example of in the history where this might have happened. This was an interesting period here in Tudor England. England kind of had two queens contesting the throne. We had Elizabeth I on the throne, and at the time, Mary, Queen of Scots, was under house arrest for 18 years. There was a plot to get Mary back on the throne. And what happened is people sent encrypted messages to her, not dissimilar to that character substitution algorithm we looked at. These were intercepted, and they implicated her in treason when she replied. Does anybody know what happened next? Yes, he just made a symbol with his hand. Basically, it didn't end very well for Mary. Okay? So pro tip here, ensure you encrypt with a strong algorithm and don't let someone get your keys. Here's another example. During World War II, the Germans used this machine on the top right here, called the Enigma Machine. By setting those wheels, you could set now up to 17,500 keys. So this was quite a lot more sophisticated than what Mary was doing. And you could just type your messages into the lower keyboard and it would tell you what the encryption thing is. It was cracked by this man here, Alan Turing. Does anybody find that amusing? Okay, that's Benedict Cumberbatch. That's actually Alan Turing on the right. And don't believe everything Google Images tells you. So that was a very sophisticated machine up on the top right, but it still suffered one problem. It's the key transmission. So what the Germans did is they had these key sheets. This sheet here on the right told you what to set those little wheels to on a particular day of the week or day of the month. If you could get hold of one of these, you could decrypt anything. So once again, just like for Mary, and just like at 500 BC, key transmission for encryption was the biggest problem ever. What happened then? Okay, remember these guys? It actually wasn't them, but I just like their fashion sense. It was these guys, Ron Rivest, Adi Shamir, and Leonard Edelman. They worked at MIT, and in the 1970s, they came up with some pretty cool stuff. The first letters of their surnames formed the letters RSA, and that went on to become a company, which has the keyring tokens, which some of you might be familiar with. What they did is they solved the key transmission for the first time since about 500 BC. They took all this crazy stuff to do with prime numbers that you learned at school and thought this is totally boring and will never be useful ever. They made that hip, and they laid the foundation for HTTPS. Now, they didn't call it that because the internet didn't exist yet. They didn't even know what HTTPS was. But what they did is, so far, what we've looked at is Mary communicating to her people in her team, and they're trying to encrypt their messages. We looked at the Germans doing the same. That's a kind of pretty micro scale. The internet looks like that. At any moment in time, there are hundreds of millions of messages bouncing around the internet that need to be encrypted. And we've seen some examples how transmitting the key so the recipient has the key to decrypt it is enormously challenging. What these guys did was they discovered, well, everything I've told you about encryption up until now relies on me taking a message, encrypting it with a key, and then decrypting it with another key. With the same key. And this is called Symmetric Key Encryption. What these guys did was to find, using some tricky mathematics, that it was possible to encrypt a message with one key and decrypt it with another. And we call that asymmetric encryption. What we tend to do is call the keys the public key and the private key. And the way it works is the public key, you can write it on your business card, you could tattoo it on your arm, you can put it on your web server. You do not care who has your public key, because the only thing that can be done with that is to encrypt messages. The only way to decrypt the message is to use the private key, and you never, ever, ever let anybody see that. So this is the basis of public key cryptography. And really, these guys, those three guys, they sort of changed the world, because without what they really discovered there, we would never be able to do anything securely on the internet. So at this point, everybody's happy. We've got HTTPS and life is good. And what I would say is that from about 1995 to 2013, it was kind of the golden age of peacefulness on the internet security. People just looked for a green padlock like that, and they moved on. Basically, all green padlocks were equal. But around 2014, I think it marked a turning point where things became a bit unsafe. We had the Heartbleed attack, the Poodle attack, the Shell Shock Bash bug. These were three prominent attacks that occurred last year, and suddenly, for the first time ever, that green padlock in your browser was under attack. When you do see that green padlock on the browser, there's a whole sequence of things going on behind the scenes in terms of the history there that, of course, none of us would ever care about, because we just want to see the green padlock and move on. But starting from 1995 all the way through to now, there's different incarnations. The only one people should be using right now is this, in 2008. It's called TLS 1.2. Already you can see up there that after 1996, the term SSL was dead. We shouldn't really be using the word SSL anymore. It was an old security protocol. So let's go out and look at a couple of people and see what they're doing. I'm a customer of Virgin Mobile. Here I am in Chrome. I'm having a look at their site. I'm about to log in. I click the green padlock and I go to the connection. Can anybody see what it says in the middle there? Yeah, TLS 1.0. Let's look at the table. Well, that came out in 1999. So Virgin Mobile could do a little bit better there. There's nothing you can do as a consumer about this, by the way. There's nothing you can do in your browser. It's not your situation. It's happening on the web server. Let's look at somebody else. I'm also a customer of these people. So they're doing a bit better, TLS 1.1. That came out in 2006. But really, everybody should be using TLS 1.2 right now. And this affects you in the room because your communication with those web servers is not encrypted to the highest standards if those web servers are not using the latest protocols. Let's look at these people. Isn't that good? They're doing okay. So Solvexia, we're using TLS 1.2. We take your security extremely seriously, and we're always trying to follow the best practices. There's a prominent Australian security researcher called Troy Hunt, and he was also interested in this kind of situation as well. He went out and surveyed all the major banks in Australia, and I've obfuscated their names on the left-hand side there, but this is in the public domain. If this interests you, go and look it up. And for every one of those websites, he went and did a rating system from another company to see how susceptible their web servers were to various kinds of attacks. And the results are pretty distressing, because people often talk about bank-grade security. And it's really just a marketing term, but what it means is like, well, if anybody's going to make sure my communication is secure, it's going to be my bank, because there's millions of dollars at stake, someone could fleece all my money. It's like, if anybody's going to get it right, it's going to be them. And what this table shows you is that is utterly untrue. If you want to go and read up on this and find out a bit more, just go to Google, search for Troy Hunt, that's the guy's name, and bank grade. And if you want to go and rate any of your own web servers to see how good they fare, what you'll end up with is a score from A to F. You can just go to SSL Labs. That's an online service that will have a look at your web server and tell you how secure it is. So we also take that stuff very seriously. That's the SSL Labs report for lb.solvexia. That's not an address that people in this room go to, but that's our testing website. So we got an A+ on that, which we're very happy with. And our production website, which some of you do use, we've got an A. So we've put a lot of hard work into hardening those web servers and making sure that we do follow the best possible security practices. Okay, so that's pretty much it. So just the takeaways are, Really, the whole internet these days should be HTTPS. There's just no reason for HTTP, but we're in that weird spot where it's still going to take quite a few years to migrate everything over. Encryption is actually quite easy. You can come up with the most diabolically complicated way to encrypt a message, but sending the key to the recipient so they could decrypt it, that was a huge challenge for about 2,500 years. HTTPS enjoyed kind of a relative period of safety from 1995 to 2013. It's under constant attack now. We already saw 3 attacks last year. That will not be the end of it. It's just going to get worse. Not all green padlocks are equal. Solvexia has a relaxed dress code. Also learned that. And he's hacked the message. The message said, what did it really say? Very good. Well done. Well done. Cool. I forgot to mention, if you wondered how I tied some of those things together, if you're a history buff, this is a great book on the left. It traces all the political intrigue of how England had 2 queens kind of contesting the throne at the same time. And the one on the right is a book about cryptography, but it's not a technical book at all. It basically just has lots and lots of amazing insights and stories from ancient Egypt up to modern times. If you're interested in these topics, they're both great books.